squared plus u plus 4x minus 21. Are we okay with that? Okay. So let's say we know that the terms x minus 3, x plus 7 generated that function. You guys okay with me on that? Okay. What are the zeros? The zeros here are 3 and negative 7. Now, what is 18 divided by 3? 6. That, when you divide something out, that and it's clean, that means it's, that means it's a factor. You guys vaguely remember that? If you divide something out and it's not clean, it's not a factor. I mean, you can divide 5, you can take 18 divided by 5 and get 3.6, but that doesn't mean that it goes in cleanly. You guys remember that? It means 5 isn't a factor. So watch what happens if you take a 0 and you use synthetic division into its thing. What are the coefficients? What's your first thing you do? You guys remember? Drop the 1. Good. Drop the 1. Multiply. Add. Excuse me. I said multiply as I was writing that. So and then I multiply. And I add. It's funny, isn't it? We just said a second ago that 3 was a 0, didn't we? 3 is a 0. That meant that if the 0 goes into the quadratic cleanly, it was a factor of it. If your 0 is 3, what's your term? Notice what you're left with. 1 and the 7. You see what that happened? What happens here is using, eventually as we get into this, probably we'll start to see more and more of this next week. But what we're going to be doing is that this process of synthetic division, what it's called, we're just using synthetic substitution right now, it's technically called division. We're going to be able to factor polynomials by finding their zeros. And if it ends in a 0, that means that that value was a 0. Remember all the times I kept talking about zeros in terms? Huh. There's a method behind the madness in my brain. Now watch this. What are the coefficients here? 1, 4. Okay. What are your factors of 27? 1, 27, 3, and 9. I can do -1 times -27, -3 times -9, so 3 times 9, and so on and so on and so on. Right? I can mix and match signs. Now, if I use a 1, I'm searching. That's not going to work. That doesn't end in a 0. So that 1 didn't work. Don't write this down. It almost worked. Didn't end in a 0. It ended in a 0, which means if 3 is a 0 of that polynomial, what term can be factored out of it? X minus 3. That means that I have an x minus 3 in that term. Well, when you divide something, you're breaking it down into more factors, aren't you? Or less factors, excuse me. Same thing goes for this. If I started with a 4th degree, this now becomes a 3rd degree here. I go again. You drop a degree. This is just getting you guys the idea of where things are going to go. -3 is a 0, isn't it? So x plus 3. What times what's 3? Yeah, together get 4. So this can be factored out to becoming x minus 3, x plus 3, x plus 3, and x plus 1. You're going to be able to use the process of synthetic division we were doing yesterday, which you just told me was pretty easy except for the stupid mistake you made. To fly through polynomial factor. Eventually. But I just wanted to show you guys the importance of being able to do, I know it's just a process thing. It's a fairly simple replicated process. And sometimes people just get like, I just rather suffocate and press buttons in my calculator. It's as much as you don't want to do, you want to do that, mastering that procedure makes your life so much easier. Yes, sir.
Why did you?
All in due time. I'm just showing where this is headed. Don't question the journey. Okay. So I'm just showing you where we're going on this one. But with today though, one of the things I wanted to do is talk about tail behavior. What's happening at the tails? The dance moves, exactly. It's our dumb dance moves. So what I want to do to start with this is get your calculators out. And we're going to go through a bunch of graphs. And what I want to do is I want to graph. We're going to do y equals x, y equals negative x, y equals x squared, y equals negative x squared, y equals x to the cube, y x to the cube, x cubed equals negative x cubed, y equals x to the 4th, and y equals negative x to the 4th. I'm pretty sure all 8 of those will fit on your calculator. Well, all right, let's do an x to the 5th then. Oh, it's so. Oh, Murphy, you're so mean by having to press buttons. Oh, woe is me. They really don't care. Okay. That's pretty funny. Make sure you use the negative button, not the minus button. All right, graph it. Oops, I need to change my window. No, my window's wrong. I'm going back to a 10 by 10. It's okay.
that's all right.
All right. It's pretty, isn't it? It's something. Now, I want you guys to take a look at. I don't know if you guys know how you can. I think if you hit, let's trace. Okay. If you hit trace, you can jump between your graphs. Oops. So you can look at each one, which color is which. Well, if we go through, let me show you this other little trick. Go back to your y equals, and what I want to do is I want to turn off some of those graphs, but I don't want to delete them. So in order to do that, you go hit the left button, so it's blinking on the equals, and hit enter, and I'll turn it off. I'm going to turn off the other 9 for right now. Quit your whining. Nobody likes that. Sorry. All right. And then go back to your graph. So, what direction does y equal x go? So positive slope, right? So it goes up and right. Maybe, I don't know. Bless you. What did the negative one do? It was the other direction. All right. What did x squared do? What did that one do? It went up, up. It went down and up. Okay, so it went up, up. What did the, bless you, what did the negative x squared do? Bless you. It went down. Okay. Bless you. Jeez. I'm sorry that you're allergic to our math today. Now watch what the x cubed did. What did the x cubed do? It went up, it went up and up. It went this little shimmy in the middle. And then, gee, I wonder what the other one would do. It'd be the opposite, wouldn't it? Maybe, you never know. Should maybe hit a button, see what happens. Nope, yep, opposite. It's crazy how this is working, isn't it? X to the 4th, if you watch that one was up, up again. It was just, yeah, you're right, it was a little skinnier. Gee, what do you think negative x to the 4th is going to be? It's going to be down, down again, but skinnier. And lastly, if you get to the x to the 5th, what were those guys doing? Aren't those also going kind of the same thing? So what I'm getting at here is your tails, as x gets larger, as x approaches infinity, positive, as x gets larger, for y equals x, what does y do? As x gets larger, what does y do? Yeah. It's getting, as x gets larger for y equals x, what is y doing? It's also getting larger. Y approaches into positive infinity. As x gets smaller, what is y doing? Y is getting smaller. As if you have x squared, as x gets larger, what is the y doing? It's also getting larger. As x gets smaller, y is getting larger. Now, when we did third degree, it came up, switched, and did this, didn't it? Doesn't that match the same pattern as y equals x? Now, if it was negative, that was the equation y equals negative x. You guys okay with that? That meant it had a negative slope. That meant as x got larger, f of x, or y, if you will, got smaller. But as x got smaller, y got bigger. There's a pattern that emerges out of this. There's a pattern that emerges out of this. What did the negative x to the fifth look like? Pretty much the same as negative x to the third, okay? So if I have negative x to the fifth, it kind of looked like this. It matched the pattern of y equals negative x. If I had x to the fourth, it looked like x squared, but it was skinnier. It matched the pattern. If I have negative x squared, it did this. If I have negative x to the fourth, it did this. There are patterns that emerge within polynomials for their end behavior. What's happening at the tails? The tails are where they're pointing in the long run. Where are they approaching? What are they heading towards? Those are all the tails. Not worrying about the middle. We'll get to the middle. The middle is how we work with all that synthetic division. But we first work our way on the outsides, learning about how the tails work. And this is where tail dances come into play. Okay, this is where tail dances come into play. If you have any function, f of x equals x to an odd. If it's positive, x to an odd, take a guess on where your tails are. Think about y equals x. Y equals x, you're dancing like this, aren't you? Isn't y to the third dancing like this? Isn't y to the fifth dancing like this? What do you think y to the 11th is going to do? Same darn thing. Okay? The tails dances always depend upon positive or negative and the exponent, even or odd. Your tails for a positive odd exponent dance. As x, and this is how most people write it, as x approaches positive infinity, f of x approaches positive infinity. As x gets bigger, f of x gets bigger. Same idea, as x approaches negative infinity, as x gets smaller, f of x also gets smaller. Tails. All positive odd exponents have the same tails. Always. If f of x is negative and an odd, what are your tails going to do? Take a guess. They're up, down, aren't they? Up, down. When I say up, down, I'm looking at it from left to right. I'm always talking about left to right. So if it's negative odd exponent, your tails are always up, down. Always. I mean, look. Negative, up, down. Negative, up, down. Negative, up, down. That always is the pattern. That's what the tails do. It'll always do that. Which means as x gets bigger, f of x gets smaller. As x gets smaller, f of x gets bigger. That always works. Always. No. There's a really cool U2 song called Always Forever. It's on their Passenger soundtrack album. Really good. We will. I'll play it. I just thought of that. Not bad, is it? Your tails always dance that way. Your tails will always dance that way. Goes also with as f of x is positive x even. What do you think your tail? What are your tails doing if you're positive x even exponent? Up, up. Think of it as x squared. Always think of these as easy as possible. X squared and x. If it's positive x, you're down, up. If it's x squared positive, you're up, up. All right? That's the idea. No matter what, these will both be, your tails will be up, up. Okay? Your tails will be up, up. Which means as x gets larger, f of x gets larger. As x gets smaller, f of x also gets still larger. I didn't even bring up the idea of this infinity symbol there. You guys okay with that? It's a hyperbolic paraboloid. You know that? It's a conic section. It's something. We need three-dimensional stuff. You can do it. There's a formula for it. I'm sure you guys all know these crazy things called Pringles, right? Did you know that they were invented by a mathematician? You know why? What's that? And that's the idea. The reason, if you think about it, yes, sir. Yes. If you think about it, what's the strongest shape in nature? An arc. Hyperbolic paraboloid. So what the guy was, he was really, really annoyed that most of his chips were always broken. Granted, I know you can still have broken Pringles. But when you stack them, they don't break as easily. Right. So the idea was he was able to come up with a press to curve them so that they wouldn't have broken chips. So I don't know, but the hyperbolic paraboloid. Yes, ma'am. Okay, so what I want you to do is think of this. Do you agree that that's y equals x squared? As x is getting smaller and smaller and smaller. For example, if x is negative 8, what's negative 8 squared? 64. What's negative 100 squared? 10,000. What's negative 10,000 squared? A lot of zeros. So as you get smaller and smaller and smaller, your y value is bigger and bigger and bigger. That's what that means. As x gets smaller, y gets bigger. We just write it in terms of x and f of x because these guys are all functions. And then the same thing goes for as we look at the negative value. Any f of x that is a negative x even, your tails are down, down. So that means as x is getting larger, f of x gets smaller. As x gets smaller, f of x also gets smaller. That's what that means. Be careful when you read this in the textbook. For some odd reason, they flip-flop f of x and x the way they state it. They say as f of x gets smaller, x gets bigger, which makes no sense in my brain or any other normal human being, because what comes first in the alphabet, x or y? X's generate y values. Y values don't generate x's. So most textbooks write it backwards. I have no flippant idea why, they just do. So this means now, if we go back to the big picture thing, and I look back at this problem, no, I want you guys to see where we're doing with this tail. Why all this stuff? Why does this matter? Well, it matters. It matters because I can look at this graph. I can look at this function, and I know what are my tails doing? Up, up. Very good. My tails are up, up. First term's positive. Exponents are even. I know that I can look at this, and I don't know what's going on in the middle, but I know my tails have to do that somewhere. Yes, ma'am. Yep. That's why we put things in descending order. That first term of an nth degree polynomial gives you all the information you need to know about its graph. Because then, eventually, like we said a second ago, we now know that we can say this is up, up. We now also know that there are 4 possible zeros. We figured out what those possible zeros were. I think it was what, -3, +3, and 1. Okay, so that means that Dave's saying that means that's where it crosses the x-axis. So I know that it crosses the x-axis at -3, +1, and 3. If there are, that means that there is what we call multiplicity, and I'll explain that as we get to it. How many possible changes of direction can this have? Yes, sir. Those were our zeros. And this is where all of this is getting to. We know up, up. I showed you guys just briefly. You don't have to find zeros yet. I'm not worried about it. We have up, up. We knew that we had those 3 zeros. One of them had what we call multiplicities. It's on there twice. And if you've got a 4th degree polynomial, how many changes of directions could you have? You have up to 3 changes. So this means that as this goes through 0, 0, that graph will look just like that. If you have a 0, it means it goes through the x-axis. If it has multiplicity, it changes at the x-axis. You've done that before. Graph that real quick. I guarantee it looks just like that. That's where all this is headed towards. We can look at a polynomial. We'll be able to generate all of its zeros. We will be able to find out their tails. We'll be able to figure out what are called local minimum, local maximums, and so on. But it starts with tails. What is happening at the tails? Pretty close. I think you have where it's flipped. I think you missed a sign. No, I'm saying it should be. I think we had our multiplicity was at -3. I put it at +3. But anyway, that I was just trying to remember what our zeros were. But yeah, it looks like that. Sorry, but because I was trying to remember what we said were our zeros 30 minutes ago, but that's the idea of what's going to happen. But it all starts with, can you identify your tail dancing? So we do tail dancing now. Yay! All right, so ready? Stand up. Yay. Where's my dancing people? Guys. All the cool kids are standing up. Let's go. You have to get up. All right, so So he does other things. Yeah, it's boring, right? I was the last class. So I'm gonna come add this to what you guys did last night. I'll collect that on Tuesday because I won't be around on Monday. We had our kids. We had nobody to watch our kids because Sycamore has a day off, so I had to take Monday off. Yeah. So because that's where we built a house because nobody in the Calvert building houses. So what I've got 5 or 6 more of the synthetic substitution stuff, and then the graphing the tails. When you graph tails, if it says -x to the 5th plus blah 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 blah, just draw arrows. Sorry. You want to hit her? Knocking her out, elbow her in the brain. I said it would have been bad. I would have been sad. Yep. So we've had. I'll show you guys